I just kind of want to start from the position. I don't know. Maybe you've seen this list of things before, but this is the original set of goals that Brian Getz had for the Lambda project, which came in with Java 8. So these kind of 5 goals that are here, and these are sort of roughly in order of importance, I would say. Um, the top 2 or 3 are kind of all essentially equal first. I mean, these 3 things kind of come together. But the expressiveness of the programming, the better libraries, more concise and easy to read code, those are all key parts of the Lambdas project. And of course, when we talk about Lambdas, that they go hand in hand with the other changes which came in Java 8, in particularly streams and default methods as well. They're really all part of the same language changes which came in as part of Java 8, which are all necessary. I think improved programming safety, yes, it's definitely a thing which Lambdas help with, but it's probably a lesser goal compared to the top 3. And then, of course, the last point is the one that I think surprised people. People thought, I think, initially that Lambdas were going to lead to a lot more data parallelism and ease of use of parallel streams. And personally, I just haven't seen it. I have not really seen any real uptake of the use of parallel streams, and I think there are some good reasons for that. But I think that the data parallelism goal, that's why it's at the bottom. It's because it hasn't really been seen or achieved in practice. Okay, so yeah, these were the goals of Lambdas. And have they done them? Well, I think the answer is very much yes, they have. Lambdas have become just ubiquitous, just everywhere for Java programmers, and they have become so much part of the landscape now for I think pretty much all working Java programmers. So let's dig a bit deeper, because you might think, okay, you have Lambdas, you have streams. Does that mean we have functional programming? Well, let's just dig slightly deeper here. What is the motivation of Lambdas? Well, I would argue, and this is sort of the entry-level requirements of functional programming. This is the table stakes, if you like. That for functional programming, you have to be able to treat a piece of code, a piece of logic, as though it was data, as though it was of value. And then what you then want is you want some nice syntax, because you don't want to have lots and lots of ceremony for writing down the inner class or whatever you're going to represent your code as. So what you want is the ability to write a small bit of code as, let's say, a function literal, and have the ability to assign that into a variable and pass it around like any other value. Now, of course, in Java, we know that there are only 2 types of value. There are primitive types, of which there are 8, and then there are objects, or specifically object references, really. A lambda is obviously not a primitive type. It's not an int, it's not any of the other primitive types. So therefore, it's fairly obvious that a lambda, whatever it is, and remember, a lambda expression, that's the full name for these things. An expression is a thing which yields a value. So what value is yielded by a lambda expression? And the only answer is it's an object. So in Java, functions, lambdas, are objects. And we can think about like a really simple case. And let's think about an object which has no fields. So just in the same way that the class JavaLang object does not define any fields. Okay, let's assume that we're going to extend JavaLang object. We're not going to define any fields on this on this type at all. And in addition to the methods of object, it's going to have one extra method. That's what we call a single abstract method, or a SAM type. Yeah, so that's kind of a useful thing, because it's sort of the minimal representation we can have of a function, because it's got just that single method. Obviously, it's Java, so we'll be doing static typing. So the static type of the method, in terms of its return and its argument types, is going to matter. But that's basically the simplest representation that we can have of what would be a function in other languages. This concept, of course, has been around in Java since 1.1, and there are lots and lots of tiny little inner classes that predate lambdas, which were basically fulfilling this role. Okay. Now, of course, with Java 8, we actually get some proper syntax for this. You don't have to write inner classes anymore. You have things like the auto conversion to the appropriate type. what's called target typing for Java Lambdas, and then of course you get also the nice effect that the name of the method doesn't matter. So this is all fine and lovely, and this is just lambdas as you know and love them today, where you've been working with Java 8. What you might not know is that underneath, the lambdas actually use an API which was new in Java 7, an API called method handles. Because you see, despite what you might have thought, and despite some similarities, lambdas are not actually inner classes in disguise. I think that might surprise some folks. Whenever I tell people this, people actually sort of, normally there's a couple of people who sort of scratch their head and think, oh yeah, actually now you mention it, they're not, are they? But some people have not thought about how lambdas might actually be implemented. And the answer is they use this method handles API, and they use a thing called invoke dynamic, which was only introduced in Java 7. It's actually the only bytecode that's ever been added to the Java specification. And what it enables the Lambda implementation to do is to actually give a lot of flexibility and a lot of future proofing and some really nice things, and not to rely upon the inner classes mechanism. Anyway, the subject of this talk is functional programming, not how cool lambdas and their implementation is. So I think I better leave that point there and move on a little. The other thing which we should also talk about is this distinction between external iteration and internal iteration, because that's also going to be I think relevant when we talk about functional programming. So just to remind you, I guess this is probably refresher code. The original Java collections do what's called external iteration, because what that means is, you call something like the iterator method on a list, and that gives you back an iterator object. And the code which is external to the collection, to the aggregate, the client code, if you like, has control. And the iterator is used to step through the collection, the list in this case, and to deal with one element at a time. So that is external control. In a certain sense, it's also exposing a bit of the internal implementation detail. Not a lot, and you don't really think of this as being encapsulation breaking, but it certainly is getting down into the detail of the business of how the collection is represented in a way which perhaps you don't want to do. It's designed around iteration. It means you have to deal with individual elements rather than dealing with the collection or the aggregate as a whole, and there's a certain amount of boilerplate and a certain amount of ceremony that goes along with it. So what's the alternative? Well, obviously, if this one's called external iteration, then the alternative approach that we're going to talk about is called internal iteration. And this is actually what Java streams do. And now you see what we're doing is it's almost like an inversion of control pattern. If I don't mean people often think about dependency injection when they talk about that. But this is, I think, a related pattern. What's happening is that the object which represents the aggregate, which now is not a collection but a stream, it has control. Control is internal to the aggregate, and the internal implementation is now kind of hidden away. This is a kind of what's happening is the programmer is saying what they want done, and not specifying exactly how to do it. If you think about the methods that are on stream, it's things like map, and map basically says, take each element, apply this function to it, and give me back a new aggregate. So notice I'm being careful about my use of language here and saying aggregate rather than collection. There's a point in here about the distinction between the collections and the streams, which is actually quite important, which we'll come back to. But the thing that I want you to take away from this is that this is specifying what needs to be done. And when we specify what needs to be done, we are talking about a function. So we are sort of implicitly bringing in the concept of functional programming because we're specifying what needs to be done. We're dealing with the collection or the aggregate as a whole, and this means that there's potentially less boilerplate and potentially less ceremony as well. So that's all pretty good. What else can we say? Well, so the question is, if we now have this sort of whirlwind tour of lambdas, do they make Java functional? Right, so do we have functions as first-class values? Yes, we do. That's fine, because we model a function as a class, and then therefore you can just have an instance of a function is represented as an object. We have the filter map reduce pattern, where you take a Java collection, you turn it into a stream, and then you can filter it, you can map it, you can reduce it, you can do other types of transformation on it. And those sort of basic functional operations are supported on the streams. That seems fine. What else can we get? Well, we can do function composition. If you have two functions with the appropriate static types, you can chain them together to build up composed functions where you apply first one function and then the other, providing the generic types match up properly. So that's really useful. All of the Java 8 code that we write, which uses Lambdas, of course, relies upon this, and everything's lovely. But my question is that enough? Does that really make Java a functional programming language? And so to answer that question, you might also want to ask another question, which is this one, which is what makes a language functional in the first place? So certainly all the things that I've already talked about. Yes, you need to have functions as first class values. Absolutely, filter map reduce and the sort of things that Java Stream brings in. That's all absolutely essential. However, I would argue that other functional programming languages, other languages which potentially are more functional than Java, have a bunch of other attributes as well. So I think that the next thing I want to do is to talk about some of those attributes. And let's just kind of build up a scorecard of how well Java actually deals with each of those aspects. So what's my scorecard? What are my criteria? Well, let's take a look at this. What have we got? 7 items, magnificent 7. Okay, so I want to talk about these things in order: pure functions, immutability, higher order functions, tail recursion, closures, laziness, and currying. So don't worry if you don't know what all of these terms mean. I'm going to define each one as we go through, and I've only got about 15-20 minutes to do this in, so I'd better be reasonably quick. So I hope I've got some definitions which are reasonably concise and which make some sense. So let's start at the top with pure functions. So a pure function, what's a pure function? Well, a pure function is a function that doesn't alter the state of any entity or object. So it doesn't change the state of an object, or it doesn't alter any state anywhere else in the system either. So the other piece of jargon that people use for this is that it's said to be side effect free. Okay. Now the way to think about this is that a function that's pure behaves like a mathematical function. So if you see an equation like y equals x squared, okay, well, or f of x equals x squared, I can put the number 3 into that, and the number 3 isn't altered by doing that. But what I get out is another number, so I get out the number 9. You can also think of things like a function, let's say from strings to ints, which is to take the length of an individual string. Well, that's a pure function. It takes in the string, it doesn't alter it in any way, and it returns a number, which is the number of characters in the string. So that would be another example of a pure function. Takes in an argument, the string, doesn't affect it, and it returns a result which depends only on the arguments. An example of a function which is not pure is the current time, because it depends upon the state of the system clock. And of course, if you call that function at different times, it's going to behave differently. So perhaps in my definition, I should say does not alter or depend upon state. That's probably a slightly more accurate way of phrasing that. I'll fix the slide for next time. So related to this is the notion of referential transparency and memoization. And this is the idea that what you can do is that you can, if you have a function call which has some parameters in it, if you know the values of the parameters, you can replace the function call with the result. So that's connected to those two last items there. Now, the JVM, of course, has no functions, by the way. It only has methods. So when we talk about Java and the JVM, we actually have to say pure methods. So a pure method in a JVM language is one that doesn't modify object or static state. So I'm just going to use the names of the bytecodes here. It doesn't contain a get field, a put field, a get static, or a put static, because those are would be relying upon external state. Obviously you can call get field on one of your arguments, but not from your own state as well. So it doesn't depend upon any external object or static state, and in particular, it doesn't depend upon an immutable state, because otherwise you could call the function once and then you could call it again, and in between time someone has modified some external state that you depend upon. So that would make your function non-pure. What's also important is that a pure method must not call any non-pure method. So if that sounds like you can do some sort of analysis where if you flag certain methods as pure, you can then build up call trees of other methods that only call other pure methods, then that's absolutely the case. You can do that. That provides you with a recursive definition, which you can use to determine statically whether methods are pure or not. It's a very restrictive set of conditions, and in practice, it's although you can do some things with this, it actually really does just highlight the difficulty of using the JVM for pure functional programming. So there's no support for it in the JDK, and there's no real support for it at JVM level either. So I think that Java probably has to be given a failing grade for its support of pure methods. Okay, never mind, let's move on. Immutability. So immutability you may well already know about. An immutable object is one that can't be immutable object can't be altered after creation, which makes the code much easier to reason about. The other way of thinking about this is that the objects have a trivial state model. They're constructed in the only state they will ever exist in. The big win is that if you have an immutable object, you can copy it, you can share it. Providing it's a simple, straightforward object, you might even be able to serialize it and move it between VMs. So immutability is a really, really good thing, and it can be extremely helpful. Unfortunately, Java doesn't have as good a support for immutability as it might do. It has final, but final is pretty fragile because it's only the reference that is immutable. You can have a final reference which points at an object which is mutable, and a final reference to a mutable object, well, the mutable object can change. So even though that your reference is holding steady, you can still have changes in a graph of objects. So all it takes is one mistake and letting a small amount of mutability creep in, and a lot of your guarantees are actually blown up. It's also worth noting that reflection can also get round finality of reference. What's the big drawback with immutability, and why doesn't the JVM really support it from ground up? Well, immutable objects cannot change state. That's kind of the point. So if you want a modified object, how do you deal with state changes? The answer is you have to create a new object. So basically, to create a new object with the changes that you want, and this puts pressure, potentially large pressure, on the GC subsystem. This problem was a lot worse in the past when memory sizes were a lot smaller, but it's still not great today. So potentially we actually will have a lot of impact on garbage collection and memory and allocation due to the fact that we're creating lots and lots of modified objects every time we want to change. For those people who are really into immutability, one of the styles is to use effectively what are factory methods called withers. Because you create your object in its state, like for example in the java.time API, you have the .of methods which are factories which create the initial states of objects, and then you can create new objects by calling these withers which start .with. So in the code example here, we set up a date in 1984, and then we can create a new object which points at December by calling the with month. Okay, so how does Java do on this one? I think we do reasonably well. Given how middle-aged Java is as a language now, I think the fact that people couldn't have predicted that immutability would become such a big thing, and dealing with small VMs and not much memory, where I think the performance impact would have been prohibitive in the early days to try to do everything with immutable objects. So I think Java, certainly doesn't get a failing grade. It may not be like the A grade that other languages might get, but I think actually we do okay on this one. Okay, higher order functions. Now this is actually a pretty straightforward idea from the point of view of Java or a language like it. A higher order function is really just a function that either takes a function as one of its parameters, or it returns a function. Now, in Java's case, that's actually quite easy, because if you think about the function type, which is present in Java util function, what that means is that a functional type, like function, for example, is going to show up as one of the generic parameters to a function. So in this case, this first example, I'm showing a function which takes in a string and returns another function. So I've called it prefixer, and what it does is you give it a string, which is the prefix, and it returns the code in the curly braces, which is a Lambda expression. So it returns a function which uses the prefix and then just prepends it on the start of the whatever string you provide it. So this is a very simple example of a function that returns another function. So this is sometimes called a generator, so you can generate functions using this. And I should also point out the syntax here is a little more verbose than it needs to be. You know, I've got the curly braces and the return statement there. Actually, you can do better than that. You can actually write it just out like this. And you know, this may look a little more complicated to read. So I think it's okay if, while you're getting used to this type of syntax, if you actually write it in the slightly more longhand and long-winded way on the line above. But these two definitions are exactly equivalent. There's just a bit of boilerplate removed. So okay, let's see how Java does on this. Well, actually, again, really pretty well. So of course you can have functions as arguments to generic types. That's how Java works. Of course, generic supports that. There is a slight hidden problem though with type erasure here. Probably don't have time to go into it today, but it's fair to say that when you start to do more complicated things with higher order functions, Java's type erasure unfortunately can give you a headache in a few cases. But still, another area, so I think this is the second one now, where we've got some pretty reasonable passing grades for Java as a language. What's next? Recursion. Okay, so what's recursion? Well, a recursive function is one that calls itself. Okay, so the standard example is a factorial function, which I think everyone's probably seen loads of times. I've written this very simple version here, where you pass in a long number n. If it's less than 0, the simple factorial returns 1. Otherwise, it returns n times simple factorial. Now, this is recursive, but one of the things that you might notice about it, if you look very carefully, is that the last thing that happens is not the recursive call. Because you make the recursive call, the value comes back, and then it is multiplied by n. So the last thing that this function does isn't call itself. The last thing that it does is multiply two numbers together. So for this reason, it's actually sort of simpler if we try to refactor and reformat recursive functions into a form that's called tail recursive. And the way that we do that in this example is like this. So we've got a little helper function. So this one's called tailrec factorial. And now we have this helper function called helpfact. And if you notice, it now takes 2 arguments instead of 1. But if you look closely, you can see that the very last thing it does is a self-recursive call. So it's now helpfact is in the form that we call tail recursive, because the very last thing the function does is call itself. I'm going to show a bit of bytecode, so don't worry if you can't read it. It's just really to show you that when you write this out as bytecode, it looks like this. And you can see that on byte 14, the invoke static, which is the call back to itself. So each time you go into this method, you're going to recursively call it. You're going to be building up frames on the stack as you go through. Okay, now if you look carefully, what you can see is that you could actually change this a little bit, because when you call help fact again, what you're effectively doing is you're just reusing this same function. So you could actually rewrite the bytecode to avoid the invoke static, to avoid the self call. And if you do that, the bytecode changes and it looks a bit like this. Because what we're doing is we're now storing the two numbers, and then we replace the invoke with a goto, which is an unconditional jump in bytecode. And what that means is we now have a place where we can get rid of the invocation. The problem with just having uncontrolled recursion like you do in the Java case is that you run the risk, if your stack gets too big, of having a stack overflow. In this rewritten version where we have a goto instead of an invoke, that no longer happens, because this code now doesn't contain any method invocations. So the stack won't grow. So you could do this. You could rewrite a tail recursive call in this way. Unfortunately, Java doesn't do that. Javac always translates a function call into an invoke. This means that tail recursion is not optimized and can and will blow the stack up with a stack overflow. Now, there are different arguments about this. In the design of Java, as it initially was, the idea was to make it transparent. If you're calling a function, which you do recursively, a function call should put a frame on the stack. The other way of saying that is that you need to have stack trace validity. You need to be able to see the stack trace frames on the stack there. This is not the only way to do it. Other languages, Kotlin, Scala, do things differently and actually do the rewriting of the invoke into the goto, which we previously saw. Not Java, however, and so it gets a failing grade for recursion. Next up, closures. What's a closure? A closure is a Lambda expression that captures some state. So, for example, a little thing like this. You see, we have our int I is 42, and then we have a Lambda expression on the next line, f, which captures it. And I appears as a part of the Lambda body, and this will work fine. If we run this code, of course, it will print out hello 42. But what happens if we uncomment the line? Maybe you know the answer, maybe you don't. So let me tell you. If you uncomment the line where we reset I equals 37 after it's been captured by the Lambda, what we end up with is a compiler error. Javac will not compile this code afterwards. It will say, hey, no, you're not allowed to do that. After you've captured a piece of state, you can't reassign to it. You can't modify the contents of that location. And so why is that? Well, in order to do that, let's decompile the Lambda. Something you might not know is that Lambda bodies are desugared. They're turned into a private static method. And then what happens is that the signature of the private static method contains any variables that have been passed as arguments. So if you're capturing state, it shows up as an argument. So in this case, we're capturing I, which is of type int. And that you can see that shows up in the signature for the Lambda body method there, because there it is. It's int. It's the 0th argument to this Lambda body. So why do we do it this way? Why is it constructed like this? Well, the answer is that Java is strictly pass by value. Okay, I actually sometimes refer to this as pass by bit value or pass by bit copy, bitwise copy. What that means is that primitive values are passed as the actual value. It's just a bit pattern. Objects are passed as a bitwise copy of the reference. It's just a pointer. So what that means is if you make a change to the primitive inside the Lambda body, it won't propagate back to caller context because you just passed some bits over. You modified your local copy of them, but there's no modification of the caller context. The other way of saying that is that the JVM has no native notion of what some languages call an environment, in particular Lisps and things like that. So if you want to modify and mutate state and have mutable state within your closure, you must use a level of indirection, such as an atomic integer. And languages that do provide pass by reference and want to have mutable closures that can change state in another context, they must provide that at runtime. So yes, Java does sort of have closures, but if you talk to some people in functional programming and some Lisp people in particular, they'll get very, very angry if you describe Java's closures as being real closures. So this one is right on the fence. This is, I guess, maybe a D-. Is it quite a failing grade? It very nearly is. But let's leave that one and move on. Laziness, a value which is not computed until needed. The JVM has no inbuilt support for these. In general, this is not an easy thing to do well on the JVM, and not many JVM languages support laziness directly. Even Clojure, which is a Lisp, and they're often lazily evaluated, or have support for lazy evaluation, I should say. Even in Clojure, you don't do laziness. You only have lazy sequences. There's no general lazy values. The only place we really do see laziness is in the Java Streams API, where the runtime has been specially designed and specially crafted to use techniques of laziness and late evaluation. So again, this is pretty close to a failing grade for Java here as well. Next up, currying and partial application. Suppose we have a function or a method with several arguments, 2, 3 arguments. What happens if we supply some but not all of the arguments to that method or that function? If it starts off with 2 arguments and you supply one of them, I would argue that what you've done is you've created a function of 1 argument. And this is the term that's known as currying. And the currying is the reduction of a multi-argument function into one with fewer arguments. There's no automatic support for it in the Java language. Java doesn't actually have a complete set of general function types. The only ones it really ships with are function and bifunction. Other programming languages may have more general versions. And the other problem is that Java's syntax, you never get the sort of syntactic sugar or the shortcuts that you do in Scala or in Kotlin. And if you are calling a function, you always have to have an explicit method call on it. So you would have to do the same thing with currying in Java. So that's not very good. But let's just take 2 seconds to see what it would look like. Here is the actual real interface for bifunction. Takes in an argument of type T, an argument of type U, and it returns an R. So it's got the apply method there. It's also got a default method. So we might imagine that we could actually add in 2 other methods called curry left and curry right. And what they do is they take in a single value and then they return a different function, but a function of 1 argument now. So remember, the function took in a T and a U. And if you curry the left argument and supply an argument of type T, well, then what we return effectively is a closure. So this is a Java closure where we're capturing the value T and returning a function of 1 argument of type U. So that basically is how you could do this. For whatever reason, the language designers decided not to do this. There's no automatic support for it. There's no syntax support for it. Java gets an F for currying and partial application. Finally, let's move on to talk briefly about the Java's type system and collections. There are 3 main issues with core Java that cause some problems for functional programming. The non-single rooted type system, i.e. the fact that you have object, which is the root of the object hierarchy, but then you have the primitive types which don't have any inheritance relationship to object. There's also the fact that we have void, which means that Java has both statements and expressions. So another common FP paradigm that people sometimes talk about is everything is an expression. Well, not in Java. In Java, some things are statements, some things return void. And that can be a problem when you have to model not only expressions, but also statements. Finally, there's the Java collections. They are large interfaces. They have many methods on them. The methods include add and remove. So all collections are implicitly mutable. That isn't great. And what people were encouraged to do before Java 8, if they wanted a collection which was not mutable, was to simply implement the mutability methods and throw unsupported operation exception from them. This, of course, is terrible because it doesn't let you know whether the collection that you're looking at is mutable or not by examining its type. And unsupported operation exception is a runtime exception. So you don't even have the exception signature to let you know that potentially this method might cause you problems. So you'd start using an implementation of a collection, and then all of a sudden you find out, oh, no, someone handed me an immutable implementation of this, and I've just got a runtime exception that's been thrown from it. So the collections are a great design from 20 plus years ago. I think if they were reimagined now, people might well do things differently. But the collections are first class. They are embedded throughout the JDK. We are carrying 20 years of history here. The streams were only added recently, and they are not first class in the way that the collections are. The collections were never designed to be functional containers. You could not realistically retrofit any kind of functional programming support on top of the way that the Java collections are written. So that's why we had to come up with this concept of a stream. And streams, I would say, are closer to being the sort of container types that we want for functional programming. And overall, I think that this is where we're going to end up. That Java isn't really that functional. A couple of the properties that we talked about earlier on, Java gets a passing grade for. But for some of them, such as currying, especially recursion, it just gets a straight up fail grade. So the key idioms like map and filter and reduce are there. But the overall effect is really that Java is, I would say, slightly functional. So we can add that to the list of properties that we can use to describe Java's type system. Static, nominal, object imperative, type erased, modestly type inferred, and now the last one we're adding in, slightly functional. So thank you very much. I hope you enjoyed the talk. I have a new book which is out in early access called The Well-Grounded Java Developer 2nd Edition, where I spend quite a bit of time talking about some of the topics that I've raised in the talk today. So if you've enjoyed it, please check out the book. There's also some great sections on Kotlin and Clojure as well. Thanks very much.